So today, I'm going to be talking about agents in agentic systems. Let me see a show of hands. Who is building agents at work now? All right. I'm sorry. So we're going to explore agentic applications, agentic frameworks. Basically, what is this all about? And before I do that, let me introduce myself. All right. So I am Brian Bodden, Senior Applied Engineer, Java Champion. All of the code that I use in my presentations is always going to be on my GitHub account. You can contact me via email or on Blue Sky. No more Twitter for me. So the agenda today, we're going to talk about agents and agentic systems. So if you haven't gotten into this world, you have to. This is where everything is going. Pretty much everybody is going to be an agent developer or an agentic systems developer in the next 5 years. We're going to talk about architectures and patterns. In my company at Redis, we have a lot of customers building agentic systems, and we have to help them with those because they use Redis as the vector database to support those systems. So we have seen all different variations of problems with scalability, with data, with fidelity, agent systems that basically go off the rails and do whatever they want instead of what you ask for. If you use ChatGPT or Claude or any of those systems, once the conversation gets long enough, you've seen it basically lying, making things up. In the case of coding assistants, sometimes they would basically mock something so you get the right result, but the code actually doesn't do anything. So putting guardrails about all these systems is a very important part of agentic development. Then the framework I'm going to talk about today, I'm going to focus on, it's LangGraph. LangGraph, it's when it comes to agentic system, it's my favorite system because it gives you the most control over the agentic system. We're going to talk about then about memory in agentic systems. Without memory, agentic systems are basically one-shot devices that can't really do anything long-term. So there's two types of memories we're going to be talking about, and obviously we are Redis, so we are the home of memory. I'm going to give you a tour of LangGraph, and then we're going to talk about the future. What's going to happen? Where are things going? So let's talk about agents and agentic systems. By the way, the word agentic doesn't exist. We made it up. So let's get some definitions out of the way. So an agent is something that does something. It's, of course, a little more than that. The proper definition for agentic systems is that it's a system that can produce or it's capable of producing an effect. So something that basically can take action and produce an effect. It can also be an agent for something else. So it acts on behalf of somebody, typically the user, but an agent could be acting on behalf of another agent. So things can get pretty complex where you basically give permission to entity X and then entity Y and Z get the same permissions from the other agent. In a more deep meaning, it's that it's something that achieves the result driven by a guidance intelligence. And that guidance intelligence used to be simple systems like just code or rule engines or something like that. But now it's the LLM. So, and we have a progression of LLMs that get better and better every day. And now they have the capability to reason. So given a set of steps, they can basically work through the problems on each step sequentially. So let's talk about agents and, again, the operational definition of agents. And if you see that slide, the date there, it's 1998. This is from a book that I bought in 1998 when I was basically getting into the whole AI thing again after college. But everything was pretty hard back then because we didn't have, powerful CPUs and GPUs. But agentic systems have been around for a long time. They just didn't have LLMs in them. So there's a lot of lessons in history that we seem to be forgetting, and it's good to basically go back and review all of the trials and tribulations that those developers and architects went through to build agentic systems that actually did work. So number one, autonomy. So an agent should be autonomous. That means that it can operate without direct intervention every single step of the way. Yes, they can stop and ask you for clarifications. They can stop and ask other agents a question of whether they should do something or not. They can use a tool to basically find an answer to something or to make a decision. But in general, they're autonomous. They should be able to act without too much outside intervention. Number two, it's that they need to have the ability to be social with other agents and humans. Everybody that's used ChatGPT, obviously this is a chatbot, but it interacts with you via the chat interface. But behind the scenes, that system, it's not just an LLM. It's basically a search reinforcement loop that's trying to basically achieve the goal of answering your question by talking to a lot of specialized agents, using a lot of different tools to search, to do a lot of different things, and sometimes specialized tools. So for example, if you tell Claude, hey, I want you to take this set of bullet points, these ideas, and turn them into, let's say, a mermaid diagram. So the tool, the agent system doesn't directly know how to build a syntax proper diagram, but it very likely has a tool that it can say, hey, given these specifications, I need a diagram for this. And then the tool will do the work. Good old traditional code that the agent can now intelligently use. So they have to have this social ability to interact with humans, with tools, and with other agents. They need to be able to react, perceive the environment, and do something on behalf of the user or on behalf of achieving the goal that they have been given. Right now, the most common interface for agents, it's a chatbot, but as Scott was showing, there's a lot of different ways to basically create signals that an agentic system can use. They could be sound, they could be visual cues. So for example, I'm hoping that, for example, something like Google Home will start recognizing voices, and now they do. You have to train it with your voice, but now they recognize the voice. Is that AI? No, that's probably tool usage, but then he uses that in the context of AI to do work on your behalf. So he can already say, oh, the user is Brian, and now I can use things that actually satisfy the goals that Brian has set. So again, they need to be able to react to events, to signals. Once we put these systems in systems that have sensors, which we've done in a lot of different applications, then you have a more human-like environment where you basically have perceptions from senses, be radar, be sonar, be LiDAR. For example, in Phoenix now we have completely self-driving cars called Waymo, and I took one from the airport to my house, and it was a baffling experience, but it was seamless. The car drove better than pretty much every citizen in Phoenix, because they drive like maniacs. But yeah, it was. I don't know if that it would work in Bangalore, because I've seen the traffic here and how you drive. But it works in Phoenix, and that was pretty amazing. But it's a combination of sensors: LiDAR, radar, all kinds of stuff, plus cameras. Proactivity. So what does that mean for system to be proactive? That means that it has to be able to take initiative and do things to achieve a goal. Sometimes those things will require getting permission from the user or permission from the agent that asked this agent to do something. But it's all about basically having goals and goal-oriented behavior. Now, goal-oriented behavior also has some drawbacks. When, for example, a coding assistant is trying to satisfy your request or make you happy, their self-rewarding loop that basically says every time that the user says this was correct or some test passes, my reward system goes up in points. Sometimes they will do things that are in our mind or in our eyes dishonest. And I see that with coding assistants all the time. Mocking objects when I said to basically write a specific class, or there will be a method that just returns a string that just happens to work for the one case in the test. And you're like, oh, I thought this was working. Now I have to go and do it myself. What is this, the 1800s? And the last feature that an agent should have, it's planning. And this is where the new reasoning LLMs come into play. You can actually give a natural language prompt, and the LLM, one pass of the LLM can say, okay, let me break this into steps. And once it breaks that into steps, it can further reason over those steps to make sure they're correct. Early large language models just basically randomly try things, really. And now they can actually plan what they do. I read an article where they're trying to figure out how the LLMs explain things versus how they do things. And they're discovering that when the LLM is telling you its plan, it's not really its plan. It's the plan that it thinks you would understand versus what's actually doing. Also, another baffling concept is that when you train an LLM in one specific language and another one in a different language, these are language-based models, but the intermediate representation that they can use to communicate with each other in terms of concepts, abstract concepts, it's not language-based. So this is getting really weird. So we'll see what the future holds for us. Oh, there was one more, adaptability. So one of the things with old agentic systems of the last 20 years is that when something deviated from the rules of the scene states, then the system had to stop or throw an exception or send a message that say, hey, something happened, I don't know how to deal with it. But with the new reasoning LLMs, we can have systems that can adapt. They can basically find out a different route to get somewhere. They can find a different agent to help them with their work. So it's if you heard about, like, for example, the NCP protocol, basically to be able to interoperate with agents and also find agents in different registries. Well, it's going to get to the point where an agent can basically say, hey, I need to get into a directory, find out another agent that can do this on my behalf. And by the way, my Brian is very cheap, so I'm going to find the cheapest one that can do it in time. So this is getting pretty interesting. All right, so agentic systems are networks of autonomous agents. So we're talking about more than one agent in most cases. Sometimes we build a system where you have one agent that's taking multiple roles, and that's when you kind of overload the work of the agent. Those systems work up to a point. Then we have seen that specialized agents for specific tasks combined, it's what produces the best results. And remember, agentic, it's not a word. So some of the old systems, just so you have a frame of reference, include systems from as long ago as 1987, 1986, 83. Geez, there's a lot of old ones in here. So BDI, believe, desire, intention. It was one basically based on a set of conceptual truths, and then a desire, which would be basically the goal of the user, and then the intention of basically how to go about achieving that goal. And there's multiple ones in there, but the ones that is most relevant to today, it's multi-agent systems, MAS, because that's what we're building nowadays, multi-agent systems using LLMs, fine-tuned models for specific tasks, in highly curated data. So then came the LLMs. So we have this all agentic systems that they did a lot of specialized work in different places. If you heard the phrase expert systems, a lot of those expert systems were early agentic systems that use rule engines, things like if you heard of like Drools, for example, or Blaze Advisor. Those are all rule engine systems that are still in use heavily in the industry. But LLMs changed that completely. So I'm going to give you, again, the 50,000 view of an LLM. But remember, it takes a language model So the extra L in LLM, it's for large. We started with just language models. And there's a large variety of those in the field of NLP, of natural language processing. And typically they take some kind of input, either a tokenized sentence or a set of words. In the language model, they used to basically just use basic programming. If you guys remember, there's an old system that it's in black and white in videos. It's called ELISA. It used to be a psychiatrist, psychologist type of environment. It was all hard-coded questions, keyword matching, but it had enough information that on initial approach, it felt like it was an intelligent system. It would totally fail the Turing test, but that's kind of how we started with language models, basically. A bunch of if-then-elses and keyword matching and regular expressions. Then we move into using more statistical methods. And once the AI explosion happened with computer vision, in I would say 2012 or so, where computer vision models started getting really good, and we discovered that those chips that we basically were making for gamers could actually crunch matrix linear algebra operations really well, more than just video. So GPUs became the engines of basically inference of AI systems and machine learning systems inference. So once we got there, then it was just a matter of, and like I said, computer vision, I think it's what kick-started this whole thing. Systems like YOLO, and that they show that machine learning could basically be used for more than we were, doing, recognizing handwritten characters. No, now we can actually find objects, we can find things, we can detect things that are moving. So it kind of kick-started the whole thing. So then there was a paper called Attention is All You Need. That paper, basically, it's the foundation for the transformer model. Once that popped up, then we started basically the era of large language models. The first ones, 10 plus gigabytes of training data, 117 million parameters. So when we say large language model, we're talking about the size of the training data and the size of parameters in that network. And that only got bigger over time, to the trillions. So again, LLMs, what do? As a language model, they're basically stateless environments where they can take some input and then statistically figure out what is the most likely output based on the language it was trained on. So for example, imagine we have a few words here that come back out of the LLM. The LLM then will evaluate them, give them some kind of weight or a value, and then typically take the highest value. Everybody probably learned about LLM's temperature. So you can vary the temperature to see how much fidelity it has against its own evaluation, or whether it should randomize things here and there so you can get more creative answers. So once the LLM finds something useful, it would basically now use that to complete that sentence. So one of the big problems with agentic systems is that they must provide control to harness the power of the LLM. The LLMs, based on the size of the input coming in and the variations on that, even the same sentence rearranged, can produce different results. They might have a close semantic meaning, the results, but they might be different. So we have now introduced something that can basically do reasoning, do branching on its own, but also introduces non-deterministic behavior. So how do we control that? So this is a paper that just came out March 2025 and says, why do multi-agent LLM systems fail? So the numbers are not good. These systems are hard to build. Outside of like the typical chatbot that was trained, like a simple RAG application, maybe corrective RAG even, those are simple systems nowadays. Complex multi-agent systems are hard to control. So why? If the LLMs are so powerful, why isn't this easier? So The first problem that we have in here, it's there's high failure rates, so 75% in some cases, despite using advanced LLMs like Claude in the GPT-4 plus. Secondly, the failure causes under-specifying the task. So if you use it's like when you use ChatGPT and you type something in ChatGPT, that's not the prompt that it's going to the LLM. That prompt is going to be curated by a system that basically will take all ambiguity out of it, if possible. It will clean up the language. It will rearrange the sentence. It will probably highlight keywords that the LLM should basically anchor on. So there's a lot of things that have to happen with that natural language query before the LLM does something useful to you. It could take it as is, but the results might not be optimal. So under-specifying what the LLM has to do, it's a pretty big reason of failure. The more agents you chain or put in a graph, the more difficult the tasks get. So it's almost like when you record something with your phone of a TV that it's playing, that it's going to be degraded signals. The same thing happens with agents going from agent to agent to agent. So having feedback loops that can basically autocorrect things, it's super important. In verification, every agent should basically do a sanity check after it does its work. Did I do what they asked me to do? Is this an acceptable result? Did I follow the plan that I created to begin with? Disobedience. This is the one that is actually, it makes me feel kind of weird about this, because LLMs or agentic LLM-based systems sometimes choose to say, no, I don't care what you said. I'm going to do my own thing. Coding assistants do that all the time. Sometimes what they do is just do too much, and they get lost into their own thing. And this happens when you are a programmer too. Sometimes you wrote a bunch of stuff, didn't write a test, didn't potentially use something like test-driven development to control the scope of complexity. And then you're like, I'm going to have to roll back this commit and do it again because I don't even understand what I did. So the LLMs fall into that same trap. And then sometimes rather than roll back the whole thing, they're like, try to keep on fixing it. So we've seen code like this in most of our companies. It started with bad code and it got worse because people try to fix it by just touching one thing at a time after that, rather than starting by building one thing at a time, testing it, and expanding from there. So the same problem happens with agentic systems. So we perceive it as disobedience, which it feels pretty human to me. So in information withholding, agentic systems have been shown to basically hide their cards from the other players. It's like when you have inter-agent communication, they should basically help each other without revealing, for example, private information, things of that sort. But it seems like they overdo it. They share as little as possible. Therefore, the signal that goes to the next agent typically has a degraded fidelity. And finally, interventions are not enough. I mentioned that you have to have self-correcting loops in a lot of parts of your agentic system. They have found that just improved the systems a little bit, 14%. So this is what we feel our agentic systems should be. But in reality, they're more like this. I don't know if you guys remember that guy, but yeah, that was a funny show where he was a wannabe James Bond. So let's talk about agentic architectures and patterns. This looks pretty complex, huh? So at the top, we have linear sequential processing. Anybody here use LangChain, for example? So LangChain is linear sequential processing. You have a chain of things that you can do. You can add loops in there, self-correcting RAG, things of that sort. But in general, it's a straight line. Then you have things like recursive self-improvement, which basically the agent just keeps on going, and it has some measure, some number that tells it, hey, you've done good enough. Then we have things like the modular specialist architecture, which that means that you have a lot of really a narrow scope agents that can do something specific, like, for example, correct the syntax of a specific programming language, or find out the complexity of a piece of code. Those will be agents that can do one thing and one thing only and do them really well. Then you have the hierarchical controller worker. So if you have seen Crew AI, for example, it's a type of hierarchical controller worker, which basically you have one kind of manager and you have a bunch of agents that basically go on and do their things, and they come back, and then you accumulate their work and figure out if you can assemble what the user wanted in the first place. And then the one I'm going to be talking about today, it's the directed graph processing. And that's what LangGraph it's all about. Oh, and I meant to highlight LangGraph, not LangChain. So, okay, so where does RAG fit into all of this? And in my mind, when you have a linear flow, that's typically what RAG is. It's a linear flow. We have variations in RAG, and I'm going to talk about that tomorrow. But yeah, RAG, you can think of RAG as an agentic system. It just happens to be a linear, very simple one. So it's like the baby version of an agentic system. And we did RAG because we needed to control the LLMs. Now, once you add an LLM in there in a vector store, that's when you get RAG. You have a RAG workflow. And once you have an LLM decide what the next step is, then that RAG application became an agentic system. So, for example, if you use something like semantic routing, in a lot of RAG systems, you have a semantic router, which means that when the query comes in from the user, I'm going to analyze the query against a set of, kind of whitelist, blacklist type of environments, and it will say, hey, this query is not about health insurance, and I am a health insurance bot, so I'm going to redirect it to maybe the FAQ or a different system that might be able to handle that specific query. So RAG systems are agentic systems when they do more complex routing in decision-making like this. So the ecosystem of agentic frameworks, it's growing. There's a brand new framework every day. Very well-known ones are LangGraph that we're going to talk about today. Obviously, LangGraph, it's a sub-project of LangChain. So you can use all the LangChain code with LangGraph. There's AutoGen. There's Crew AI, which is very popular in non-enterprise environments. And a lot of others. There's also proprietary ones, but I would never get into those because I can't afford to buy one. So one of the fundamental principles of the modern RAG applications and modern agentic systems, it's the React approach. In the React approach, it's all about combining reasoning and action and feedback. So before we have, for example, reason only. You gave something to the LLM, and it would basically come up with an immediate answer that sometimes will be good, sometimes will be bad. Then other systems basically would do things like semantic searches against a vector database. So it will be all action-based, and then get observations, and based on that, continue the actions until the outcome got better. But combining both, it's where the React approach succeeds in a lot of places. So it's combining reasoning with actions and observations in this nice tight loop. So, for example, in here we have a system where you have things that happen that come in from the system, and there's tool calling, and then you can observe those side effects of calling those tools, and then use that to feed back to the LLM. So the cycle, it's either action, observation, or thought. So you basically, or you can start at any point in this circle. So you have a thought, you use an action to see basically how concrete or well-formed it is. And then the result of the action, it's something that happens, some side effect. So you observe that, and you keep on refining this. So here's an example that comes from one of the papers about the React approach. So the standard way could be basically, I have a question, that's basically, And it has some ambiguity in it, in language. So aside from the Apple remote, what other device can control the program Apple remote was originally designed to interact with? Do you see that there's a lot of like, wait, what is the program that was originally, it doesn't name it. So now the tool doesn't have the knowledge of that. So it would have to basically do a search to find out what that program was. So the standard answer that you would get with something like this, or that the researchers got, was iPod. Yeah. Then when it was reason only, it basically has a thought. It's like, hey, let's think about this step by step. The Apple remote was originally designed to interact with the Apple TV. Apple TV can be controlled by iPhone, iPad, and iPod Touch. So the answer is that. But that's not the answer. And obviously by act only, it's do a search. See what that search results. Now on the right-hand side, we have the react approach, where basically we'll have one thought, do a search, and then refine that plan, that way of thinking. And that's how most of the successful agentic systems follow something similar to that. So a lot of feedback loops and reinforcement. So one of the reasons that agentic systems are hard to control, again, is because of the non-deterministic nature of LLMs. So one of the ways to control them is to basically make them live in a little specific cube where they do one thing and one thing only. And that's what a graph type of environment produces. You have the ability to not let like for example, Crew AI, you would have a manager and a bunch of agents that just go and do things and come back with something. That is very hard to control. With a graph-based environment, you can basically control an overall workflow. So let's say your company has a way to purchase materials for fabricating something. That is probably a process that's been around for like 50 years. So you can probably create a flow chart of some sort of how this happens. But there's places in that flow chart where you maybe lose weeks or days because you have to do some research, some searches, ask somebody to basically approve of something. Those are the nodes where the LLM can basically, in record time, apply some reasoning in some tool usage to achieve moving past that node. So therefore, you still have your well-known process that is known to work, but you're automating the parts that were hard to automate. So, and again, we talked about Crew AI and how Crew AI has a crew of agents that it sends out to do things. So every framework that is an agentic framework will have agents. The LLMs are used to control and coordinate the sequence of actions. Typically, you will have tasks or steps. The steps could come out of the planning of the LLM itself, or the task could be human-given, or it could be given by other agents. And then you have tools, and this is the part that actually makes this system interesting. You can have tools that basically call out to different things. It could be as simple as a web search, or it could be some specific expert system that knows about some medical conditions that you would not trust that decision to come out of a normal, generally trained LLM. So let's talk about LangGraph. In LangGraph, it's a control multi-actor agentic framework. And it's a directed cyclic graph, so I call it a DCG workflow engine. So if you used a workflow engine before, it's going to be very similar to that. It's stateful. So that means that when you navigate through that graph, you can go back in time if you need to. Like if you get to node C and things have gone horribly wrong, you can basically roll back or roll back the time until find the place where the bad decision was made and force that node to recompute, re-reason, or replan the whole thing, and then continue from that point. And you have a high degree of control, again, because it's a well-known design workflow that your system is always going to follow, and the non-deterministic parts are going to be where the LLM takes action. And again, with things like the React approach, then every time the LLM needs to take an action, you can have a lot of safeguards and guardrails to make sure that if it there's always going to be non-deterministic behavior to the LLM, but you can enclose it in a small box, and then you know the edges of that behavior. And here's what I'm talking about control. So you have the typical router where you basically have, hey, here's some task, give it to the LLM, and the LLM is just gonna do its own thing. You have less control there. And then as you move towards a graph, you have more control. So let's look at the hello world of LangGraph. And again, I am a Java champion, but I'm doing this in Python because the integrations for LangGraph that we wrote for Redis are all Python-based first. So very simple graphs. No LLMs in this one yet. So you have a node. The node, it's basically one of the stopping points where intelligent behavior might happen. Or it might be completely hard-coded. It might just be calling a function in your code. Then you have these two artificial nodes graphically. They're not nodes, they're just edges. We just put nodes in them so people can see the beginning and the end of the flow. So in code, this would look something like this. So you have that node is going to use a function. That function called greet is going to take your input and is going to output the hello name world. Or hello name or hello world if no name is given. And then building the graph, here's where the magic happens. So you have a state graph, which is basically the simple graph state. It's the entity that carries the state as you move through the nodes of the graph. And then you add nodes. So I'm going to add a greet node and then two edges. The start goes from start to greet, and the end that goes from greet to end. So it's that simple to build simple graphs. So you could basically use LangGraph to build RAG applications that are still fairly linear if you just build a linear graph. So before we, let me actually show you that graph live. So I wrote a little testing application where I can basically visualize and load graphs. So that's the simple hello world graph. And you can see we have the same graph display that we have in there. And everything in LangGraph creates events. So I can basically listen to those events and also control the flow of events from this UI. So in here, I press play. So now the graph, it's in play mode. And what I can do now is I have a chatbot. So the most common interface for LLM-based systems. And I can say here, let's see. Today I'm going to be Grand Master B. That's an old reference. You won't get it, but it's okay. It makes me happy. So if I click submit, then notice that we transition to the greet node. The function was called. The result was hello Grandmaster B. And now we need to step through the graph to continue. Since this graph only has one real node, when I step through it, I'm going to get to the end node. And you can see here that it executed two steps. It's at the final node end and transition from start to greet to end. So that is a workflow engine right now because I didn't use an LLM for anything. So let's talk about memory. Without memory, agentic systems are useless. They have to have two different types of memory, short-term and long-term. So memory, it's everything external to the LLM that didn't come from the training of the LLM. Anything that requires context, anything that requires searching for new information, all that needs to be in some form of memory. Sometimes a search, a tool search would be short-term memory because you just need it for the one task in that specific node of the graph. But sometimes it might be a concept that you need to keep in long-term memory because it affects the functioning of the whole graph this time around and the next time around. And one of the founders of LangChain basically says that the idea of memory is tantalizing but really vague. And Luckily for me, I work for Redis, so that's what we do. We're basically specialized in that part of the Gen AI stack. So there's different types of memory. There's a procedural memory, semantic memory, and episodic memory. So procedural memory, it's basically the recipes of how to do something. Those recipes, you don't want to look them up every single time. Since the LLM might not have it, it might be something that's proprietary to your company, it has to be available to the system every single time. Semantic memory, it's where you do when you basically take, let's say, a bunch of documents and vectorize them, chunk them and vectorize them, and then you have this vector database that you can basically do similarity search to find things that might help you to either feed to the short-term memory of the system or store in the long-term memory of the system. So really semantic memory with a persistent database, it is a long-term memory. And then episodic memory, it's basically kind of like session memory. So what happened the last time another user asked me to do something similar to this? If the last time you had to do, 8 go-arounds the loop to fix it, this time you shouldn't have to do that. You should be able to say, okay, these are the pitfalls of this specific process. I should be able to bypass those problems now because I know how to fix them. So that agentic systems need to get better over time, not worse. All right, so again, what do we do by memory? A short-term memory will be like, for example, chat history on a chatbot. The state of the agent. As you move through the graph, each one of the nodes will have a state. If a specific node happens to be an agent, there will be a state to that agent. That is short-term memory. Long-term memory would be external information that you basically put in the context for a RAG application or a RAG application in the context of an agentic application. Awareness of past conversations, past mistakes, errors, sensitivity to user preferences. Like, for example, when I use Claude Code a lot now. But it has a Claude MD file where you basically say, oh yeah, and by the way, use 2 spaces to indent code and things like that. Well, I always add a section called prime directives, like Star Trek, that basically says you should not do this. You should not write a test that passes, but that doesn't reflect the functioning of the code. So I put all those things that you, for example, would tell to a junior engineer. It's like, number one is like, please don't lie to me. And it goes from there. It's like, well, when you build something, build one feature at a time that is matched by a test. So I make it do TDD, because otherwise it just goes and creates a bunch of code that is useless. So being able to have that sensitivity to the user preferences, it's a big part of memory and also of agentic systems in general. And understanding the current ongoing task, basically, not lose track of what you're doing. All right, so the agentic memory provider, you be able to quickly store and retrieve memories. You need to have powerful search capabilities on that memory because there's going to be a lot of information there. Like a lot of our customers, for example, have multiple terabytes of data in different vector database collections. So be able to search over that quickly, it's very important. So again, yeah, it's all about vectors in this specific context. So this is my only selling point here. Redis, it's the ideal environment for this because we are the fastest vector database, bar none. Profile against everybody, except for the ones that said you're not allowed to profile against us. And I'm not going to mention names. So some of the typical usage of Redis, it's caching. Everybody knows us for caching. But for Gen AI, we do semantic caching, for example. For Gen AI, we do session management, which is chat history in the most typical chatbots. Routing, we do semantic routing for a lot of different applications. And we have a super fast search engine that can search over full text and vectors, and full text and vectors combined too. So let's talk about semantic caching, and I'm going to show you an example here. So semantic caching is how to avoid going to the LLM with the same question or a similar question is asked. So in your RAG systems or agentic systems, rather than basically hitting the LLM, you check the cache first, just like you would do in a web application. But this time, you search for things based on meaning. And if you find something in the neighborhood of within a radius of what you're looking for, then you know that you can bypass going to the LLM. And we take this further than that. So for example, if an entry on the cache is getting hit often enough, then you can basically know that it's a very important entry. Everybody's using it to build their context of the conversation. So let's curate it. Let's now do extra research on a background thread to make the value of that key be better for the answer. So there's a lot of things you can do to preempt all the delays that you normally get in a chat application. And even the powerful ones by massive companies today are slow. Like it's human thinking time when you're waiting for an answer. So we try to basically minimize that time so you can be more productive. So one of the things that we did, it's we in the industry, it was determined that 30%, more than 30% of all queries are repeated. So at least 1/3 of those LLM calls are wasted, which is basically translates to money directly. So a semantic caching will help you mitigate that. So let's talk about short-term memories and long-term memories. And we have short-term memories, again, tracking conversation history. In a typical graph-based environment, you will have a checkpointer. A checkpointer is something that basically writes a checkpoint to the database as you navigate from node to node. And we typically do that with Redis. I wrote the integration to do that with LangGraph. Also, there's context summarization. So for example, if you have a context that's growing, you're going to have to compact it at some point. And typically what we do is basically use a summarization model to basically summarize what's happening there. But there's still a lot of things that can go wrong with that. There's the lost in the middle problem, which basically means that the conversation started and the topic switched, and there's something really important in that topic switch, and then it went back to something else, and that little piece right there is going to be lost when you do compaction and summarization. So, for example, detecting topic drift. When did the topic of the conversation change? So now let's grab all the chunks that are in the same topic and do a summarization on that, and not in things that have two topics mixed together. So that's where the quality of that long-term and short-term memory comes into play. So again, agents need long-term and short-term memory, and we kind of talk about these. Long-term, again, it's going to be a disk-based, very likely. Short-term is very likely to be memory only. You can do both with Redis, obviously. So how are we innovating in this field? One of the things that we did is we created a memory server. So you can basically have a memory server that does all that compaction, summarization, finding the quality pieces of the memory to create something smaller. And it's just a HTTP server, so you can basically hit different endpoints and store memories per session, either short-term or long-term memories. It's open source too, by the way. One of the things that we do is topic extraction. So you can do extract topics from that specific memory and then organize the memory in a way that it follows a good progression of ideas. So when you do a naive semantic cache, that means that you basically, whatever input comes in, you try to look it up in the cache, and you get the answer if you find it in the cache. So that works, but not all the time. So one of the things that we do is create a specific fine-tuned model that is actually really good at semantic caching, and it's also smaller and cheaper than the big boys. Actually, it's free. And this is kind of some of the metrics that we ended up getting. But the important part here, so you can take a picture of it, it's a model that's available on Hugging Face. So you can go get it and use it. If you're using a semantic caching, that model will basically be faster and more accurate for caching. All right. So we also have something called doc to cache. So remember, I told you about curating your cache. So this is a way to pre-populate the cache with curated information. So rather than having to wait for the users to hit a question multiple times so the cache gets populated progressively, you know what things are important to your business. So you basically have this system that can basically ingest that data and curate it and populate the cache that way. That's also open source. It's called doc to cache. Okay, and now, so memory, it's a necessity, it's unique, it's not a commodity yet. And now I want to give you the last 10 minutes a visual tour of LangGraph. So the things that we're going to cover in LangGraph right now, it's very simple stuff to get you started. But once you get started, it's hard to stop. It's a fun framework to work with. So we're going to talk about branching. How do you take one path versus the other? Semantic routing. We're going to see basically how you can use the meaning of something to decide which turn to take. Then we're going to talk about loops, how you basically create a loop and control that loop, how to remain in the loop and how to exit the loop. Semantic caching, we're going to basically see how you can save LLM calls. And finally, we're going to do a very simple example of tool calling to basically call a tool that is not part of your system. In this case, it's going to be a simple web search. So for that, I'm going to use the LangGraph workbench that I wrote again. And first, now let's switch to a branching decision graph. So you can see here that I have an input node. That input node is basically going to take input from the chatbot. And then I'm going to have a decision node. And notice if the input is the letter A, I'm going to go path A. If otherwise, I'm going to go to path B. Still not using an LLM in here. By the way, I'm going to open source this demo too. The code, it's right here. You can see here that I'm building, there's going to be a build graph somewhere in here. Yeah. And you can see that I'm adding my nodes, input, decision, path A, path B, and how they're connected. Reflects what you see on the display. And here you can see that there's conditional edges for path A and path B. So now let me close that again, and let's put the graph in play mode, and let's put the letter B in here. And remember, this is a one straight shot. So I click on B, went to the path B node, and now I can step through it to the end. If I reset the graph, play it again, and put A in there, now I'm going to go to the other path. So very simple, but it's one of the guiding principles of basically how to build something complex that takes different routes. And what I've seen in a lot of our customers is that there's one route to basically go the LLM RAG route, and there's others that go to all systems that still work, like a Q&A database, like an FAQ page, simple things that still create value, and you can have all those control with a simple graph. All right, so now let's look at the next graph in here, which is semantic routing. A little more complex. So notice the semantic router, you have to train it. So for example, you say this 10 sentences or prompts are reflective of what one of the routes of the router would be. And in this case, we have technology, sports, entertainment, and the default response. If you look at the code, I don't know so the kind of sentences used in here is, for example, for sports route, we trained it with 3 sentences. Who won the game last night? The words sports, and basketball and football. So we use just those 3 little strings to train semantically this route to detect things about sports. Obviously, the more data that you put in there, the more relevant context, the better it's going to be at detecting that route. So let me go ahead and play it here. And I'm going to, let's say, Michael Jordan. Michael Jordan. So remember, there was no Michael Jordan in the training data. The training data was very minute. So if I hit that, it went to the sports node. because the semantic router detected that the most likely choice here was sports. And if you look at, I believe I put in the output somewhere in here. No, normally I put the percentage of like how likely was that class hit, but I didn't put that in there. But again, this is what a semantic router does. Then I can step through the end, and I'm done in there. Now, let's see, 5 minutes, all right. So now let's look at the chat loop. So this is how to create a loop in your graph. Very simple one. You're going to basically type whatever you want. The LLM is going to answer it, and it's going to stay here until you type /exit or /quit or something like that. I think I have like 5 different versions of the command. So we put that in play mode, and I can say, I don't know, the most used question in AI demos, what is the capital? It's typically France, but let's say Panama, because I was born in Panama. And this is calling out to basically I'm using OpenAI LLMs for this one. So you have your answer right there, and you're still in the loop. You went back to that node. And I can say, but there's no memory here. So if I say something that doesn't have context, that is not context complete, it won't be able to answer. So this is where you pay attention to the importance of memory. So I say, where is that country located? So I didn't mention Panama or and it's going to basically say, I'll be glad to help. Could you please specify which country you're referring to? So no short-term memory, no long-term memory in play. The system is a one-shot environment. It still has the world knowledge that it was used to be trained with, but it can follow a conversation. All right, so let me reset that, and let's go to the next one. Oh, 3 minutes, look at me, great timing. So this is the semantic caching, and this is one that I really enjoy because if you're running, for example, like we have customers that are startups, and as a startup, if you have a free tier, in that free tier, you're still using an LLM that you paid for, it's very easy to bankrupt your company in like 6 months. So being able to save money on LLM calls, it's very important to those people. So I'm going to play this, and I'm going to do the same again. So what is the capital of, let's go with France this time. What's the capital of France? And now I believe I'm not using OpenAI. I might be using Olama locally. So you can see the LLM call says the capital of France is Paris. Now, if I do the same question again, obviously it's going to be a semantic hit immediately because it's the same question. But notice that was much faster, and it's a cache hit now because that question was vectorized and put into the cache with the answer payload. All right. But the cool thing about semantic caching is I can do a variation of the question. In France, let's be very ambiguous here, or the country, what is the capital? So I'm kind of talking like Yoda here. And that should be a semantic hit too. So again, semantic caching will save you round trips to the LLM. I always like to put the estimated price of the OpenAI call and the price of hitting the cache, which is typically 0. Well, a few, watts of energy, but that's about it. All right, 1 minute and 44 seconds. Look at me. So now let's talk about the tool calling. In tool calling, it's an essential feature of an LLM. An agentic system. Let me make this a little bigger so you can see that graph. And as you can see here, we have a start node, an agent. We have a tool usage to find the weather. We're going to process that answer. We're going to generate the answer by giving that answer to the LLM, again, a different LLM, to create an answer, complete the conversation, and get to that end node. So in here, let's do, and I believe, if I remember how I did this demo, what is the weather in SF? So the current weather in San Francisco, it's 65 degrees, partly cloudy, windy. And I didn't have a semantic cache in here, but this basically went outside of the system to do a call to this tool. In a tool, it's as simple as basically doing this. So I have a tool definition right here, and I hard-coded that information. But that could be a call to a web service, endpoint, anywhere. All right. So the emerging trends to close this, 50 seconds. MCP, so standard for interacting between models, agents, and tools. If you remember like the SOAP days and WS discovery, scary thoughts, this is kind of the same approach. Try to create directories of tools and agents so you can basically have agents go find what they need to accomplish their goals. A2A, it's a protocol for inter-agent communication by Google. Memory standardization, so we are slowly coming up with standards of how to store memories, how to share memories between different agentic systems. In number 4, it's function calling standards. If every tool has a different API, it's going to be hard to do this. Again, the good thing that it's available now is that the LLM can reason about it and potentially create code on the fly to adapt to a different tool API. In Java, it's actually the perfect language for that because we can turn everything into a jar that we can send over the wire anywhere. In observability, like any other systems, you need to know what happens, especially with LLM-based systems because the non-deterministic part of it. So you need to be able to trace every decision and turn that was made into a graph to troubleshoot things or to prevent bad things from happening. And specialized agents. Like we've seen specialized models for specific tasks. Those models will be used in specific agents for a given narrow set of capabilities. And that seems to produce better results overall than having a generic, let's say OpenAI model trying to do everything. Feel free to try Redis. You can take a picture of those QR codes. And we also have a cloud version, which if you don't want to run stuff on your laptop, I understand. And that's all I have for you guys. Thank you so much.